This lecture is concerning shear strength theory, and we're going to try to tie up some loose ends that we've had in some of the earlier lectures. A lot of the stuff that I put in front of you didn't make a lot of sense then, will hopefully make a little more sense now. That photo you see is from Knoxville, and that there's a little history behind that. I might, this is a good opportunity as any to put that down. I first taught at UTC in the fall of 2001. It was right, in fact, 9/11 took place right after I started the semester. And we were in Grody Hall at the time. And Grody Hall was, at the time, was old and unrenovated. And it was a really rough place to teach, particularly where they had me in soil mechanics. We didn't even have a lab then. We had to do virtual labs, and it was not the greatest situation. And so so we were, thanks to the efforts mostly of the then Chancellor Bill Stacy, we managed to get approval to fund the building that we're in currently, which is it's traditionally engineering, math, and computer science. Now it's a computer science building, which was completed in 2005. But into preparation for that, one of the things we wanted to do was to equip a soils lab. So Dr. Ueno, who was himself fairly new to UTC at the time, came and I went to Knoxville, which is where I took that photo. And we're given a tour of Knoxville's lab by Randy Rainwater, who is a fairly well-known geotech in the Knoxville area, who's now, I think he's back in private practice. So it was located in Estabrook Hall, which is in the shadow of Neyland Stadium, and it was old. It was really old. And so we get through there, he gives us a tour, and finally we sit down and we see the old equipment. Well, the equipment was, mixed. The old, we looked at all this stuff and the facilities they had. And so Randy asked us, what kind of budget do you have? And Dr. Ueno's response was, what budget? Well, we eventually got a lab, and I first taught that in 2005. And we've been doing soils lab ever since. So that's how that happened. Let's review soil strength. Tension in soil is seldom, if ever, used. Even in rocks, we have to be careful about using tension. Sometimes the problem with rocks is different. With soils, actually it's the same problem, but it's different. It comes out differently. In soils, we know we have a discontinuous medium going in. We got a granular medium. With rocks, you've got fissures, which act in pretty much the same way. Fissures don't take tension, just as the voids between soil particles don't take tension either. So we don't do that. We stick with compression. The most important failure mode to consider is shear failure. We normally, Mohr Coulomb failure, we talk in mechanics and materials about different failure theories, and I've mentioned this once before, but we're using Mohr Coulomb failure theory, which is actually the maximum shear, let me try to make it, one of the most common theories of failure that we use is maximum shear stress. Not we think in terms of tension, strength, and whatnot, but basically when we actually get down to brass tacks, the maximum shear strength failure is what we use, or to call it by its proper name, the Tresca theory. The only difference between Tresca theory, and we actually use Tresca theory in soil mechanics in certain soils, and Mohr Coulomb is the fact that Mohr Coulomb adds the effect of the internal friction of the soil. Otherwise, they're the same. So we're using Mohr Coulomb is a maximum shear strength theory of failure, even though it is not the maximum shear strength theory of failure. How it acts in the soil depends on the soil type and also the way it's loaded too. So we need to ask the question, what constitutes soil strength and how do we test for it? And to a large extent, and they're not, the two questions aren't related, but they're not identical either. The development of testing methods and the development of the theories of how we work are pretty much they're twins somewhat. They go together, but they go together. And part of the challenge of soil mechanics, and I think in the career that you are entering it on, I think one of the challenges we're going to eventually face is coming up with a different failure theory for soils, and at the same time testing it, and at the same time getting it through all of the hoops you have to jump through, particularly in this country, to get new methods accepted. That's going to be the big challenge for soil mechanics, I think, in your career lifetime, is going to be doing this. There are others too. For example, a few years back we had a professor at UTC who had a method where you could actually put a soil into a machine, and using lasers, it would tell you its angularity and particle size of the soils, which is a major advance from the sieve analysis, although you won't necessarily get the same result. And if such a method ever got adopted in the general scheme of things, it would revolutionize particle distribution analysis of soils. But right at the moment it hasn't, because all the methods, everything is geared by regulation and whatnot towards using what we've got. So there are a lot of interesting things going on in soil mechanics. In my opinion, the biggest problem getting from here to there is going to be, first of all, convincing everyone or getting a consensus that these methods are in fact better, and some methods are better than others. We have to sort out which ones really work and which ones really don't, and then get the testing and the regulatory environment, the testing environment and the regulatory environment to accept them. Those are the challenges we have in geotechnical engineering moving forward. Let's talk about different particles. One of them is the angle of internal friction. It will vary from, it varies because by particle size. Generally speaking, smaller particles have lower angles of internal friction. But there are other things. Relative density, of course, is part of that. The closer packed together, they're going to change the internal friction. Angularity of the particles, whether they're angular, we talked about that earlier in the semester. The gradation, particle size, of course. It says particle size 3%. For a specific type of soil, yes. But in the general scheme of things, smaller particle soils have lower internal friction. And that is the big thing, really. So that slide is interesting somewhat, but not necessarily the most informative thing you ever wanted to have. So what kind of test do we run? Direct shear test, triaxial test, UC test, unconfined compression, fall cone and vein test. And we're going to talk about most of these. The fall cone you see more in Europe, although we're starting to see it more over here. Start with the direct shear test. That's a direct shear mechanism. There's actually one sitting in our lab. We've never used it. It's the obvious. When people think of shear, or as my Virginian, one of my machine design friends, shear, you basically think of things feeling like this. In other words, where you apply, a stress like this, and it eventually shears it. So basically what you do for soils, you construct a box. And you split the box in half, and you push one half of the box one way and one half of the box the other. Because this is a granular soil, And because its strength is dependent upon what, the pressure that it's under, you have to have a normal force, which you see by N, on top of it. And you can measure the shear strength. The problem with it, there are certain situations where the direct shear test is what you need. It depends entirely on how soil fail. It assumes that this is the proper way for soils to fail in shear, I guess, but they don't normally do it that way. Normally speaking, shear stress failure takes place when the normal stresses get to the point where you remember Mohr circle. If you have large principal stresses, the principal axis said they got with no shear in sight. You rotate that 90 degrees and you got maximum shear. Whether you have shear or not depends entirely on, it's not a fluid, it's not hydrostatic, it's not hydrostatic fluid, so you're going to have shear stress somewhere. The failure is reproducibility is problematic. You see it in some cases, but generally speaking, if direct shear had solved our shear test problems, life would be a lot simpler. The test that is used more often, and I want to be, I don't get too deeply into this because it's easy to get very deep into this test, is the triaxial test. Probably one of the most important tests we have in soil mechanics, but it's also one of the hardest to run properly and to get decent results. Basically, it's pretty simple in concept. In the middle of this, you've got this soil sample, which is usually there's a membrane around it, rubber membrane, and it's a cylinder. And it's put between two pistons. Well, this is a stationary piston. This is the moving piston. And they're usually, the pistons have drainage possibilities. There's porous bead on either side. Whether you drain it depends on whether you open and close the valve. And you progressively apply, you pressurize the chamber to some confining stress. And that confining stress can be used, among other things, to replicate effective stress effects. And then you apply a load to it and you wait until see it failures. And failure usually means it bulges out, or it can do across the old 45-degree thing where it fails, plain like that, and you have failure. The thing that has changed most often is the drainage. So, for example, you'll notice in sigma 3, which is the confining stress, it's always held constant during this test. In an unconsolidated, undrained test, a UU test, the drainage lines are closed, and the stress gradually increased from the confining stress. That's the simplest one: unconfined, unconsolidated, undrained. In a consolidated, undrained test, it's gradually increased from there, the same, and no water is permitted to escape, and pore pressure is measured for effective stress test. Last but not least is the consolidated drain. Very gradually increased from the same one is very gradually increased, and the drainage lines are open. And the thing that keeps it coming out, obviously, is if it's a clay, then you've got the low permeability of the clay, which keeps water in. That is the fast explanation for a very complicated test. And we're going to really just sort of scratch the surface of it. You could do an entire course on the issue of the triaxial test. And there's another summary of it. You'll get different types of failure. It's very much like any other compression test. If you get a brittle failure, like you have on the left, then it comes up and then stops. It hits the maximum deviator stress. And the deviator stress, if you recall, is the difference between the sigma 3 on the one side, which is the confining stress, and the maximum compression stress, which is sigma 1, and then it fails. With a ductile failure, you can actually get up to its top and then it comes back down. And there are many different failure modes in this. So how do we use the triaxial test? One of them, the most important one, is to determine the failure envelope. Now, I talked about the failure envelope earlier with Mohr Coulomb theory, and we talked about using the multiple circles. And this is where we do it. This is where it happens. You will start with several samples from the soil that are basically the same. If they're not the same, there's not going to mean anything. You start run one at a confining, at a low confining stress. Low being picked by your lab, and you're a geotechnical engineer, and you run into failure. Now, failure can take place in any number of ways, but Beroit mentions one. I kind of brushed through it here a minute or two ago. We have a 45-degree angle. If you recall, again, from Mohr's circle, I'm being repetitious on this, you're kind of trying, your underlying assumption in triaxial test is your principal stress is this way, your first principal stress, your third one is your confining stress this way. Well, shear stress theory, if it follows maximum shear stress theory or Mohr Coulomb, then that means that the failure surface is 45 degrees out, because on Mohr's circle, the maximum shear stress points is 90 degrees out. So you get that failure very often. Then you finish one assessment. Then you put another one in, you ramp up the confining stress, you start it again. You get that. And you might do it 3 times. You get third one, you ramp it up again, you run it again, you get failure envelope. And the idea is that all 3, if you draw a tangent line through all 3, and that's the tricky part, then you will get a failure. You'll get the phi value, and where it intersects with the y-axis, you'll get the c value. And therefore, you can determine its Mohr Coulomb properties. You can do this for any number of conditions. You can do it for either drained or undrained conditions. Note, again, this is definition of deviator stress, and I've gone over this several times, but there it is graphically. For multiple stresses, that's pretty much what I've just gone through. You can use you could actually, what this represents is there are 2 different specimens, and I started with sigma 3 as my initial stress, and I increase it. And I increase it to the point where I hit this last, it hits the failure envelope and produces failure in the specimen. Or actually, it's the other way around, really. I increase it till I get failure in the specimen, then I compute the failure envelope. And I do this twice. The idea of cohesionless, and sometimes, again, we do it for different drainage conditions, because actually these properties can change with the drainage condition of the soils. For cohesionless soils, in theory, if I know that a soil is really cohesionless, I could do this in one shot. Why? Because a cohesionless soil, by definition, is C is equal to 0, which means the failure envelope passes through the origin. If it passes through the origin, then I only need one test to do that. It's actually, we've got the tangent of a line, and then a tangent, point, tangent, I can get the envelope. With a cohesive soil, and we're going to come back to this with the UC test. In theory, and this is particularly true with unconfined, in theory, for a purely cohesive soil, Mohr Coulomb theory tells me that no matter what the confining stress is, the shear stress, or the cohesion, the C value, this one right here, is the same. because for a failure envelope, if you recall, this is the phi value, this angle right here. If phi is 0, then this line is going to be horizontal. If that line is horizontal, then all of these circles, no matter where you run them, are going to be the same. Now, you'll also note here something else. You'll notice that the Q is equal to sigma 1 minus sigma 3 over 2. And sigma 1 plus sigma 3 over 2, here's the P. This is really, I'm kind of leading you into a PQ diagram using that. Because PQ has some advantages over the traditional sigma tau diagram for this particular. And then you got some combination of both, and those are always the fun ones, because you have to run multiple tests to find out, because you've got both C and phi are greater than 0. And this is kind of another, the friction angle. If I ran 1 here, I'd have it. And I know this is for a mixed soil. You would have the friction angle here. Notice carefully that sometimes failure envelopes are not straight lines. They don't always turn out that way. We can maybe be able to approximate them that way, but they don't turn out that way. But the fact that they're not straight can tell us a few things. One of them is that, and this is what, is that we have preconsolidation. If we have something like that, that means that we have different strength characteristics at different confining stresses or effective stress conditions, which gives us an indication we have preconsolidation. This is what I was talking about with the cohesionless soils, and we actually take advantage of this when we get the UC test. This is a stress path diagram using the PQ diagram. And this is your classic PQ diagram. Usually that's where the PQ diagrams are used most often, is with stress path analysis. And stress path analysis is something I'm not going to get into in this course, but it's important frequently to determine, if we have a stress history, we may be able to, it may be easier to predict what the soil will do if we go in there and add to the stress history. For purely cohesionless soils, the shear strength, again, is equal to, has no C, is strictly a function of two things: the internal friction angle and whatever confining or effective stress is on it. This is important because you cannot have, a cohesionless soil requires some kind of surcharge or precharge to get any strength to it. There are different, however, there are also in soils with cohesion, there are two types of cohesion. There's true cohesion, which is due to cementation, electrostatic and electromagnetic attractions we talked about in the early part of the course. There's also apparent cohesion. Some cohesionless soils, if you've got negative pore water pressure like you have with capillary rise, you will get apparent cohesion. The soil will look like it has strength, but when the water goes away, the strength goes away. Classic example of that is on the beach. If you've got soils with some moisture to them, they will stick together better than they will if they're just dry beach sand. However, if you dry that beach sand out, which is clumpy and wet and moist, it will lose that strength. So you do not rely on that for design purposes. And again, purely cohesionless soils. Now, let me talk pure cohesive soils, excuse me. All the strength of the soil is developed from the cohesion soil in a purely cohesive soils. And sometimes cohesive soils will actually, because of remolding and whatnot, will actually transform themselves into mixed soils. And the triaxial test can be used to predict that or to quantify that. There are two different factors that we have in cohesion, in two different quantities. unconfined compression strength. If it's QU, what it means is that it's the difference between that and that, the unconfined compression strength. I'm going to talk about the unconfined compression stress, so we determine the unconfined compression strength. That's the difference between the confining strength and the full. The cohesion of the soil is half that. It's the shear maximum shear strength, the distance from here to here. In other words, this. And normally speaking, it varies by a factor of 2 by this equation. Very frequently in problems, you will be asked to compute, you will be given either the unconfined compression strength or the cohesion or shear strength. Don't get them mixed up, or you will be in big trouble by a factor of 2. And a lot of correlations. Sometimes they will list correlations as unconfined QU, sometimes they'll list C, or sometimes S. Don't get them mixed up. Soils with both, traditionally, ideally they're one or the other. And there are certain fields of geotech, like deep foundations is bad about this, where we just kind of say, well, they're either cohesive, and a lot of our methods are based on that, and that's really not true. But we treat them that way, and because traditionally deep foundations are driven into previously undisturbed strata, we can get away with that. Disturbance of soils will tend to shift them more into a mixed category. And of course, you've got soils which are iffy because of their particle size composition, dirty sands and that sort of thing. Let's consider the undrained triaxial test example. Given a dry cohesionless soil, tested to determine its phi, where confining pressure is 720 psf, the deviator stress at failure is 600 psf, and the pore water pressure at failure is 496.2 psf. And we're going to find the value of phi drained and undrained. That's interesting how you can do that without draining it. So that's part of the reason why we keep up with the pore water pressure, is so that we can actually estimate what would happen if we actually were to drain the pore water pressure without actually having to go through a drain sample. So we go to this. Let's do a little math first. This type of thing is always giving geotechs a chance to show off that they did not bomb trigonometry. Sigma 1 is equal to, there are two components to the failure stress. One of them is the cohesionless component, this one, and the cohesive, this one. If I were to solve for the sign of phi from this, I would get this. However, since I'm dealing with I know that it's a purely cohesionless soil, I can get rid of this term because C is equal to 0, and I get this. If I take this and solve for that, I will get this. And you will see these equations again in a place you're not expecting them. So with that in mind, I do a little of that. I can actually solve for phi strictly from the if I know the confining stress and I know the failure stress. Now, for the undrained condition, I just take the data I have. It just means that sigma 1 is equal to sigma 3 plus the deviator stress. Delta sigma d is the deviator stress. It is, as I keep, the difference between sigma 1 and sigma 3. So sigma 1 minus sigma 3 is equal to deviator stress. I was given both of those. I simply plug and chug, and I get a sigma 1 in the undrained condition at 1320. I'm not going to take any consideration for the pore water pressure. Now, since I've done that, and since I put phi is equal to the arc sine of that, I simply plug and chug into that, and I get a phi of 17.1 degrees. Okay, with that in mind, I then turn around and the drain condition. What's different about the drain condition? The drain condition means is that effective stress, remember, is total stress minus pore water pressure. So what I want to do is I want to compute the effective confining stress and the effective failure stress. And I do that simply by subtracting the pore water pressure at failure from each. That's how I do it. So I take 7, in this case, instead of, and this is prime drain conditions, minus 496.2 is equal to 23.8. I do the same thing for the failure stress. I take 1320 minus the same thing. I get 823.8. I substitute just as I did before, and I get 34.94, almost 35 degrees. So the drain conditions give me very different results from the undrained conditions. I give another granular soil, unit weight 19.6, internal friction angle 35. Whatever proposed structure I'm putting on top of this causes the vertical stress to increase 60 kPa at 4 meters of depth. Also consider it the case where the groundwater table increases the ground surface. Find the shearing strength 4 meters below the surface before installation of the structure. Whether the soil will shear with additional load, and whether the shear will soil with additional load at elevation of the water table. There's a lot of different ways of doing this problem. The way that I recommend is compute the failure function to see which side of the envelope this thing is on without having to make any assumptions or without having to back compute the location of the failure envelope. So, okay. In case 1, the soil overburden pressure is 78.4 kPa. That's strictly dry, 19.6 unit weight times the distance. So that sigma becomes sigma 3. The additional stress, sigma 1, is the deviator stress, which is actually the additional stress I put on top of it. With the deviator on top of that, I get 138.4. So that's my sigma 1. Case 2, the soil overburden pressure is, the water comes to the surface, total stress, or actually I'm doing it the same way, it's just a matter of rearranging the algebra. It's basically 19.6 minus 9.81 gives me the submersion unit weight of the soil, times 4 meters is 39.2 kPa. And then 39.2, you add 60 to that, you get 99.2. And so therefore, I have a situation where I've got 2 sets of principal stresses. And all I need to do, since I know from the previous that C is equal to 0 and the internal friction angle is 35 degrees, I take the failure function and simply apply it to both. I have 2 sets of sigma 1 and sigma 3 and 1 value for phi. And C. I simply plug and chug. By direct substitution, the first case, the F is minus 64.4 kPa, which means it's in the failure envelope. And case 2 is minus 19.4. Now, in both cases, it's within the failure envelope. But the second case is closer, and that shows you the general effect of raising the water water level in the ground decreases the effective stress, and by doing so, it decreases the soil strength, particularly in cohesionless soils. Cohesionless soils are a little different, obviously because by Mohr Coulomb theory and in practice. So, so therefore, the second one should be given greater care because obviously I'm approaching the failure envelope. The last one is a problem which I'm not going to go into it here. I actually, 2 samples. One of the, I would, I'm not going to do it here. I actually go into it on my website where I talk about PQ diagrams. PQ diagrams are the best way to solve these problems. The reason why that is for one thing, you don't have a lot of circle tangent issues. Circle tangent issues are a pain with regular tau sigma diagrams or sigma tau diagrams. They're really a nuisance with those diagrams. They just don't really do that. They're hard to do. I mean, you can draw some circle and whatnot, and with CAD you can get exact results. The other trout in the milk is this. This one only has 2 data points. Many cases with a triaxial test you run 3 data points. Now, 1 or 2 things is going to happen. One of them is that you're going to notice nonlinearities. We talked about that with the pre-consolidation stresses. The other thing that could happen, and when I say only things that can happen, well, I really should not say that. I should say 2 of the things that could happen. The other thing that could happen is that you've got 3 points on the PQ diagram. You know, your circles on the sigma tau go down to 3 points that are reasonably in line. But, it used to be we would draw this line kind of and do that. There's no really simple way to get the 3 circles to line up, even if they're close. There's no really concrete way to do that. With a PQ diagram, what you do is you simply use your spreadsheet's trend line method, or you can do it by hand. And for those of you having fluids lab, remember that. And you can actually compute the slope of that line and the y-intercept of that line, and then can translate them back into C and phi simply by 3 points. And you have the best solution. Statistically, that's the best solution to the problem without having to wonder, well, did I draw this right or stuff like that. It's statistically the best solution. And that's why I recommend using PQ diagrams, particularly for, now in this case, you will get a definitive result because what you're, instead of having, with only two, you are doing an interpolation. With 3, you're doing a least squares regression for a linear correlation. And of course, if you've got nonlinear problems, you can play around with those too. Unconfined compression test. One of the things I mentioned is the fact that no matter what the confined pressure is on a purely cohesive soil, the deviator stress, the QC, and the C are all going to be the same. So somebody says, why do we have to have that? So let's just get rid of the confining stress. It simplifies the test a lot, and the UC test is very useful for purely cohesive soils that we know are purely cohesive. We can get their cohesive strength very easily using the unconfined compression test. And in fact, we've done this in our lab. There are other methods of determining shear strength, and we're going to talk about some of those. We're going to shift more to in situ test. If you can accomplish the same thing with an in situ test that you with a laboratory test, you're better off with in situ because of the sample disturbance. All the tests I've talked about up to now, direct shear, triaxial, unconfined compression, all require undisturbed specimens. There's the old typical values. For cohesionless soils, these are reasonably decent. These and they are dependent upon grain size. They normally assume well-graded soils, but you have those data there. For preliminary work, they're definitely a nice thing to. They're definitely a good thing to have in interpreting, and for sometimes with boring logs are the only way you've got, depending on what data that they actually took in the field. It's important to have, and that of course underscores the importance of a site boring plan. You lay out the site board, you survey a site, you say, we need to have this, 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 and this, and you don't miss anything. But sometimes in this profession, we get thrown at problems where we didn't develop the boring log plan and we need some information. Sometimes these are very useful. This is a little bit more sophisticated for cohesionless soils. Your book has this chart in a little bit more legible form. And it shows the for dry unit weight versus angle of internal friction for different for different classifications of soil. It shows you what you would expect in terms of the dry unit weight, relative density, and all that good stuff. So this is very handy to have as well. For cohesion, it's more of a crapshoot, really, for cohesive soil. For preliminary purposes, they still have to be used with care. Preliminary purposes is something you would not want. You would not really want to hang your hat on this unless you really don't. These can vary wildly depending upon the nature of the clay and whether it's moist or saturated or whatever. So you have to be careful using these. The vein shear test, and we discussed this, I mentioned this earlier, I'm going to come back to it. Really, it's a very simple test. It's basically you've got, tradition. In the old days, when you first started, you had the hand crank vein shear test. And you would crank it and get a torque out of it. As I said before, you take this looks like the back end of an arrow. You stick it in a rod, you go down. Now we have much more, even that looks old, but it's still computerized where you've got the torque, it gives you the torque, and you stick it in there and it does it. That's a lot better. And that's one reason why I think the vein shear test is finally coming into its own in terms of being used. But it's fairly simple. You bore a hole down or do it at the surface, depending on what you're interested in. You then stick the sheet in and you rotate it one way to determine the strength, get the torque out of it, and then you rotate it back around to determine the sensitivity of the clay. Which in areas where you've got sensitive clays is important. Field vein shear test calculations are somewhat straightforward or not that complicated. The CU can be as 2 times the torque over this expression. It's a function of the torque you get and the geometry of the veins. It assumes a uniform shear strength distribution in the vein. Unless you hit a layer, you can probably do pretty well with that. But if you've got rocky soils, you got to be careful with it. But for a reasonably uniform soil stratum, uniform I say within a few inches, it's fine. And then the only thing you may want to correct for, and this is easy to do because you almost always take Atterberg limits with a boring, the correction for the plasticity index is there and should be only used for embankments. And then all you do is you have a corrected C sub U is equal to mu, which is this vector here, times the uncorrected value. When you remold it, you turn around and go back. You get another value for another torque. You can determine if the 2 torques are pretty close, you don't have a very sensitive clay. If you have, which means the sensitivity is, if you've got something where you go back and the clay just turns to mush, and you don't get any torque or very little torque. I've spent too much time in the field. Very little torque, then you've got a very sensitive clay. This is sort of a quick summary of tests, and it can be very useful. I want to do a production note before I conclude this lecture. The way that these lectures were done, the first 2 lectures that I ever, the thing that sparked this this whole videotaping of lectures and whatnot. It's not no videotape here really, but videoing these lectures was the invasion of COVID. And the first two lectures I did are the next two lectures here, which are for slope stability and lateral earth pressures. And those were done back in March of 2020. And those will be your next two lectures. And those are strictly lectures where I actually do slide, actually just, you don't even see me. I'm just shooting slides up and doing an audio commentary on them. And then the next ones I did were for the foundations course, which they did during the summer of 2020. And I did it in this format. I find for me personally, this is the easiest format. I want to try to replicate what I for better or worse, I want to replicate how I do it in class. And then, of course, most of the lectures in the fall, I've tried something else in the early part of the semester, but I wasn't really happy with it, so I went back to this. But in any event, the next two lectures are strictly slide with commentary lectures, so don't be surprised if they're different from what this is. But in any event, until next time, thanks for watching, and God bless.